can help you make yours better. Grab homework, please. And by homework, I mean the 2 days ago one that has to do with blood type.
Wait, did I do?
Yeah.
Okay. Let's start with the easy side. The long lost son side, right? Mr. and Mrs. Cash. So what's the story here? We have a mom who's, wait, what's dad? Is he AB? Yeah?
Yeah.
Okay, so Mr. Cash, we'll start with the pedigree. Mr. and Mrs. Cash, he's AB, she's A.
Yeah.
And then there's someone claiming to be a kid, and their blood type is what? O?
Yeah.
And it's a boy, right? So there's your pedigree. They want you to do Punnett squares. Well, okay, we can do that. But we have to do, they want you to do 2 Punnett squares because of her, because there's 2 possibilities for her, right? She could be, either way, he's A, B. So that's how that's going to work. But she could be AA or AO. The Italian genotype. Okay. Hey. Oh. That's if she's AA. This is if she's AB. Are any of those possible genotypes O? O is going to be 0, the double O, right? Yeah, so that's not a thing that could be true. This is, by the way, this is all we had before like DNA testing. We could basically say, no, that's not your kid. There's no way that could be your kid. But we didn't have anything we could actually confirm. Yes, that is. It was like we could just rule some people out. So DNA testing has brought us a long way. That's the easy one. Let's look at the big old pedigree. Let's see how you did. I think I told you, but if I didn't, this is how you should do it when you're doing blood types. It's a little different from other problems. We tend to write their actual blood type inside the square and circle, and then write their genotypes under. Right. So this is just what we were told, what we know about. Shoot, I don't even remember all. I got a little creative with the names, I think. Johnny and June. That's of course Johnny Cash. They do have a kid named Roseanne. Patrick Cash was a tennis player. Yeah. Okay. So let's see what we can figure out. First of all, who do we know for sure? Who shows us their genotype right off the bat? Which blood types? We know ABs, right? So we can take any ABs, of which there are only 2, and just say, yep, their alleles they've got are A and B. No problem. Who else? What other genotype do we know for sure?
O.
Oh, yeah, because O is just 2 recessives. And it's really the O's that are going to get us through this. Okay, where do we go from here? This is so, I mean, it's all the same trick, right? Recessive kid.
Both the parents are AO and BO.
Recessive kid, dominant parents. Doesn't matter if it's co-dominant, right? For them to have this kid, it's the same story. Both of them, even though they've got one co-dominant, also have to have a recessive. It's the only way they can have Patrick. Yeah? Okay. What else? Where do you go from there? What was your next logical step, Riley?
The parents of the kid. So the very bottom left, the parents of those kids have to have an O.
Same story. Big A, big B, gotta each be hiding an O for them to have those two kids, absolutely. Okay? This is gonna be relatively easy here. I don't think, how many question marks did you wind up with? Any? None? Yeah, I think we can do all of this. How about, can we do this, kid? Kid/mom? Not from here, but from above? How does that set of parents have a type B kid? Can she be this? No, because where would the other B come from? There isn't one. So clearly, she's not that. She's this. Good? I think maybe we can figure out these two. Well, hang on. The A works out because we know that A came from here. So what does this have to be for him to be only A? This has got to be the O from here. So we know that one. This, there's a big B. Could she be BB? Could she be BO? Okay, well, there's a question mark. And we don't know that one. Riley.
So there's the AB parent and the A parent. Would the A parent have to have an O since the grandchild had an O and the daughter had an O?
Ooh, this kid right here.
Yeah.
Where did that O come from? There's only one spot in there. Yeah, you're right. This A has to be AO because that has to be where that O came from.
And then would the A and the B also be AO?
This one here, let's see, could, no, because I think it could be AA or could be AO. There's another question mark. Yep. This one? Are there two A's to be had? No, it's got to be AO. Is that everybody? Two question marks, that's not bad. She did it right, she just did it wrong. Okay, so now let's get to the real question here, now that we know everybody's genotypes that we can. Shortly after a huge inheritance is announced, Rhonda, Donnie, and Denise, I was up late, claiming to be their uncle Hezekiah, the previously unknown son of great uncle Patrick, that's this dude, fathered with a traveling circus clown named Ha Ha. There is the theoretical Ha Ha. The theoretical line down to Hezekiah, whose blood type is AB. Okay? What do you think? Abby six.
No.
No, why?
If they were to, even if she was AB or had one, it would have to be O on the other side.
That's good. I like how you said even if she's AB, because that seems like, okay, that might do it, but no, right? Even if Ha has AB, she can't give both of those alleles to this kid. She gives one or the other. The only options with this pairing is a type AO or BO, and he is neither of those. He's an impossible child of those two. Good. So, liar. Awesome. Feel good about blood type? Okay, your last pattern of inheritance is coming. Grab your notes. Nope, that's actually hemophilia. Go backwards for that. That's it. Now we keep. Honestly, I do this because I feel bad that you're getting the wrong impression about eye color. So the last pattern of inheritance we're going to do is actual real eye color. To see how it actually works. Again, it takes two new patterns of inheritance to explain them. It's kind of like blood type, and then we've got a couple of new things happening. First of all, eye color is one of those traits we call polygenic, which means it's not just one gene that controls it. It's polygenic in a way that allows us to actually do genetics problems with it because there's only two genes that control it. we get into really polygenic traits, it becomes a nightmare and we can't touch them without a computer because something like horse color, believe it or not, horse color, for you horse people out there, that's the one that has the most genes I've ever seen in an actual genetics problem. There are 11 genes that control what color a horse is. And you got to know all of them if you want to predict breeding outcomes. Eye color's nice, there's only 2 genes. You knew there had to be something weird, right? Because we kept doing problems like, okay, well, brown is dominant to blue. And you were like, what about green? What about hazel? What about the colors you're not talking about? So here's what about that. First of all, there's more than one gene, there's 2. Second of all, and by the way, with more than one gene, we're going to get a range of phenotypes. Usually with a polygenic trait, when there's a whole bunch of different genes controlling one trait. Like human height, but first of all, is kind of the classic polygenic trait. How many human heights are there?
Wow.
Sort of depends on how you subdivide, right? Pretty much almost infinite number of different heights you can be, right? Somewhere between 2 feet tall and 9 feet tall. Those are the extremes. Well, if I were to graph that out, a polygenic trait like height, and this was, height. This is like 9 feet, and this is like 2 feet, and this is just number of people who have each height. What's the graph going to look like? Where are we going to find most people? So, like, what? I think women are something like 5'5" average. Men are more like 5'8". So we're going to find most people. We're going to find the highest number of people in kind of this area, right in the middle. As we go this way to taller and taller, what happens to the numbers? Yep. As we go this way towards 2 feet, what happens to the numbers?
Bell curve.
Wait,
What's it called?
A bell curve.
Yeah, unless you're a statistician. In which case they call it, it's so common in statistics, they call it the normal distribution.
Really?
Yep.
Huh.
So yeah, we tend to see a bell curve with polygenic traits. We tend to see a kind of a middle ground where most people are. And then as you move away from that on both ends, falls off. Right.
wouldn't it height lower because of like toddlers and stuff?
Well, no, we're talking about full grown height. Yeah, not. But here's what's funny, Riley. If you measured 3-year-olds, if this was all a graph of 3-year-olds, you'd see the same thing, except this would be like 4 feet, or 3 feet, or however tall 3-year-olds are.
Tiny.
I don't remember. Okay. Good, but eye color is easier than that. It's just two different genes. So there's no, well, it'd be like a bell curve with 3 points on it. The other pattern going on here is called epistasis, because it turns out not only are there 2 genes controlling eye color, but one of them totally covers up the other. You can probably guess which eye color is going to be the one that covers up other eye colors. Yeah, it's brown. It's fairly predictable. So, human eye color, here's how it works. We have one gene, which is on chromosome 15. You don't have to memorize that, but it's true. It's the 15th of the 23 pairs. It's called the OCA2 gene. Don't worry about what that stands for, just the name of the gene. But that's the one, if you want to simplify eye color, that's the one you're talking about. It's brown is dominant and not brown. It's does your iris secrete melanin, which is that brown pigment that works on skin as well. Does your iris secrete a bunch of melanin when you're like 7 or 8 months old? You know that newborns all have blue eyes, right?
What?
No, there's so many weird things about babies. Have we talked about? We did. I had a rant
We talked about that. They're gross.
Yeah, they all have blue eyes because they have not secreted their melanin yet. I don't know. Mine were both like real pale blue. And I was like, oh, we got 2 blue-eyed kids.
I get it off.
Well, that's you though. So here's what happens. The other gene called GEY, yeah, is on a different chromosome and codes for green and blue, and green is dominant to blue. But you don't even see that second gene unless you're recessive for the first gene. This brown, the darker pigment, makes it so you can't see green or blue pigments. You see how this works? You have both genes. You have a genotype for both genes. But if you have even one big B for that first gene, the second gene is invisible to everyone. Can't see it. So we call that, we use the word epistatic. The dominant OCA2 is epistatic. It covers up the GEY gene. So if you got big B, or big B, little b, if you're homozygous dominant, or heterozygous for the OCA2, for the brown, not brown gene, you got brown eyes, no matter what's on GEY. Only if you're recessive. Only if you're little b, for that first gene, do we then worry about your second gene. And what happens is that if you're little b, big G, or big G, little g, that's a green-eyed person. And only if you're littles all the way through, 2 little b's, 2 little g's, that's a blue-eyed kid. Without any of this, these don't turn on until like 6 to 8 months into babyhood. Your eyes are blue as a newborn. If the OCA2 turns on and you secrete brown stuff, what color do you think the GEY protein is? The thing you secrete to make your eyes green instead of blue.
Yellow.
It's a yellow pigment. Good. Yeah, brown just covers up the blue, but yellow tints the blue so that yellow and blue make green.
Thank Mrs. Saab for that one.
Excellent.
Is it like that in animals too? Because when I got my kitten at first, he had like bright blue eyes, and now he has like brownish green.
I would imagine it's the same deal. Yeah. Yep. Okay. So that's it. That's maybe, I don't know, the most complicated thing we've had, but it's not. I mean, you know how to do a 2-trait cross. It's the same deal. Try one. Grab a piece of paper. I want you to cross 2 heterozygotes for both traits. I told you we were not coming back to Punnett squares. I lied. I want a Punnett square for this one. Give me a Punnett square of this. Remember, this is B's and G's. So this is someone who's big, little, crossed with someone who's big, little. This is not new. You've done this before. It's just a 2-trait cross. It's going to go the same way that, you know, eye color and height at the same time went, except when you get to actually interpreting the square. So let's see if we remember how to do the big 4x4 Punnett square. Go ahead and give it a shot. Okay, most of you are remembering. A couple of you have slid back into the way you did the first time we did this, the way you did it wrong the first time. Make sure make sure, don't write that, make sure that every row and column has a B and a G. Right, because we're going this and this. So we got, okay, big, 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 little, big, little, right? That's what it looks like. Not new. This is, we've done this before. You did this on a test already. Most of you nailed it. The good elves and the bad elves. Remember? Okay, so it's gonna. Now's the part where we have to count who looks like what, right? Okay, how many brown-eyed kids? There's 16 total boxes. Count how many of them are brown-eyed. Circle them.
12 kids are brown-eyed.
She says 12. You guys agree? Is that how many? So you're expecting 9, right? We're used to 9 to 3 to 3 to 1, but this is different because Big B covers up whatever else you have. So we have our normal 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. But it turns out that this one is also brown, and 11 and 12. Those are all brown-eyed kids. So 12 brown-eyed. How many green-eyed? Gotta have 2 little B's and at least 1 big G. Well, that applies to this one, and this one. 3 green-eyed kids. And of course, now we're down to the 1. So our phenotypic ratio for 2 heterozygotes for both eye-colored genes is going to be 12 to 3 to 1. And just like our other 2 trait crosses, that's as complicated as it gets. As soon as anybody's homozygous for anything, your square should get smaller. If you understand this, you save yourself work, and your square gets smaller. Okay, get out the first set of advanced genetics problems I gave you. I think it says genetics problems 4 on it, maybe. Yeah, IV, Roman numeral 4. Had the big hemophilia pedigree on the back. What you're going to do now, want you to circle number 4 and 5. And then 8, 9, 10, 11. 4 and 5 are blood type problems, which is what we did for the last one, just reinforcing that. And then 8 through 11, those are all real eye color problems. That is your homework, okay? Just 5 problems, 6 problems. The blood type ones should be easy. The eye color ones, there's one that's a lot like this. And then everything else should be easier. And see if you can move from Punnett squares into pedigrees with this one. Okay, yeah. 4, 5, and then it's just 8 to the end. 8 to 11.